Dr. Kaushik Roy is a Edward Tiderman Jr. Distinguished Professor of Electrical and Computer Engineering at Purdue University. He received his bachelor's from IIT Kharagpur and PhD from University of Illinois Urbana-Champaign. After working at Texas Instruments on FPGA and low power design, he joined Purdue, where his research now focuses on neuromorphic computing, machine learning, and energy-efficient circuits and architectures. He has supervised over 100 PhD students and co-authored 2 books on low-power CMOS design. He previously led the Center for Brain-Inspired Computing and currently leads the Institute of Chips and AI. Today, he will talk on cognitive computing, its robustness and security challenges. So please join me in welcoming Professor Roy.
I have 2 speakers, it seems, or rather 2 microphones. So what I'd like to do today is talk about some of the work that we've been doing in the recent past on neuro-inspired learning. So going all the way from, you probably know that in neuromorphic computing, data is all important. I'm not going to be spending a whole lot of time on data, but on sensors, algorithms, and hardware. So we have seen a huge amount of progress in deep learning, right? You open up any tech news today, there's always a news about AI and deep learning and how great deep learning is. And some of the ones that are actually kind of interesting. This is from some time ago in CNN Business. It came out that AI won an art contest, and the artists are furious. So that really means that AI was really doing well compared to the professional artists. But if I were to really think about the biological systems, there's a huge difference today. And despite the tremendous progress that we have made in AI, the biological systems still have a functionality which is unmatched with artificial systems. And this is an example of a fruit fly, which does amazing things. You want to swat a fruit fly, it flies away, moves around very quickly, figures out where it is, right? And it all does that with a mere microwatt of compute power. Just a little bit of, But on the other side of it, we had a project in the Center for Brain-Inspired Computing, and our collaborators, UPenn, they developed what's called a flying monkey. It can't even do the kind of things a fruit fly does, but the compute power was about 1 to 2 watts. So that sort of tells you, the gap that exists today. On the other side of it, if you go a little bit further and say, hey, what's the, if I were to look at humans, the power consumption sort of is of the order about 20 to 30 watts. But if you really look at the kind of things, this is actually from the Go, competition that AI won. It turns out that they required about, thousands of CPUs and GPUs and had about 10 to the 6 watts of power consumption. So there's a huge gap between what the biological system does versus what the artificial system can do. This efficiency gap is also clear. In fact, we did some case study on a smart glass where you can wear this smart glass, and that uses some state-of-the-art accelerator like a Google Edge TPU and so on. And it turns out if you do that, and we implemented sort of a RetinaNet for DNN, a deep learning network for object detection. And it turns out that under ideal conditions, the battery life would be about an hour or so. Now, if you consider display power and all those sort of things, the battery life is probably going to be less than half an hour. So it's almost like every half an hour you have to change your battery. So that's not sustainable. So the question, of course, is we certainly have existential proof that the brain is really good, right? So what are the inefficiencies? Where do these inefficiencies come from in our artificial systems? The inefficiencies come certainly from the fact that we don't certainly know the algorithms of the brain, right? The kind of algorithms that are used for learning and for inference. The hardware architecture of the brain is certainly quite different from what we know of the standard von Neumann architecture. We don't really have a CPU on one side and memory on the other side. It's all mixed together, and a lot of computing is done in the memory itself in some interesting ways. That's not quite understood. And on the other side of it, if you think about the circuits and devices, today's workhorse is basically the CMOS transistors. They're good as switches, but turns out when you try to implement, for example, synaptic functionalities or neuronal functionalities, they may not be very efficient. So there's a need to rethink some of these circuits and devices also. So to that effect, if I were to really think about coming up with a efficient system to do these neuromorphic operations like object detection, flying a drone going from point A to point B, with proper sensors, turns out the kind of things that you have to look at is, first of all, hey, what are the kind of sensors that I'm going to be using, right? And we'll see later on, we'll be using the sensors to be cameras and different kinds of cameras. So can I really fly from point A to point B as an example, say with just the cameras? What are the learning algorithms that I need to have? What sort of network architecture that I need to look at? Now, once I have such network architectures, they need to be implemented in a hardware. So what kind of hardware is suitable for such algorithms? And finally, at the end of it, as I mentioned, the circuits and devices should be able to efficiently implement my neurons and synaptic functionality as well. Now, and as I said, we certainly know that brain is reasonably efficient. So can we take some cues from the brain? And what are the cues that we can take from the brain that we can efficiently utilize? So to that effect, one can potentially think of the neuron models. And most of these standard neural networks, they look at a very simplified model of the neuron. So the neuron model turns out to be important. Can I take some cues from the learning algorithms? What kind of learning algorithms that the brain uses? Whatever little that we know. How about the network topology? So if you really look at the visual cortex, do I know the network topology of the visual cortex as an example? And today there's a good amount of work that has been done in the visual cortex, but do I know much about it? And finally, the computing principles of the brain, right? And so as I said, it's not like a von Neumann computing architecture. So if I were to go a little more into details of it, turns out, the neuron models can be quite I'll go into a little more details of it, but the neuron models can be, for example, a discrete spiking neuron. It could be, for example, a sigmoidal neuron, or an activation function could be, tan hyperbolic kind of functions. What makes sense to use? That turns out to be important. Now, how about the learning algorithms? The learning algorithms, people usually today use what's called backpropagation, and I'll very quickly talk about backpropagation, but it turns out in the brain, people have noticed some sort of local learning. Is it possible that I can use some of those local learnings? Another area that also requires a good amount of attention is the fact that if I'm using my eyes, we do what's called the glimpses or the foveation. If I'm just looking at you, I can almost ignore everybody else. So not all pixels are important. And most of deep learning today uses every pixel to be as important as any other pixel, right? But and we also at the same time have something called the saccades, which are rapid eye movement. So I can quickly go out, scan this room, figure out, where the people are. So is it possible that I can use, in my learning, some sort of foveation and saccades, just like what the brain does? On the other side of it, as I mentioned, the network architecture. So what should the network architecture be like? Should there be local connections? Should there be some global connections? Should there be feedback connections and so on? So those are very, very important. But can I figure out the right kind of network architecture? And finally, as I mentioned, the computing principles of the brain. Should there be integrated compute and memory? What kind of communication should I have? Should it be event-driven computation? Because if there are spikes and I'm doing computation with spikes, should I really have computations when there are spikes available? So should this be an event-driven hardware that I should develop? How about the inputs that I would have to my system? Should it be analog inputs? Should it be a different kinds of time-based coding that I should use? What kind of input is going to be good to my system? Or in other words, what kind of input should my sensors provide to my network architecture? So to that effect, let me go a little more details of into this neuron models and the learning algorithms. I'm not going to spend much time, but sort of let you know what are the things which are being done today and what are the possibilities to make it more efficient. So the neuron model, if I have to look at a biological neuron model, basically there you have the neurons and the synaptic connections, right? And whenever there's a spike that comes in, the membrane potential of the neuron goes up. And if there are a lot of spikes that come in, the membrane potential goes up, and beyond a certain point, the neuron fires when it reaches a threshold. Now, if there are no spikes, then there's a leak that happens, and the leak turns out is actually quite important in forgetting things. So that's, can I efficiently utilize such functionality? And that certainly, I mean, a system like that can be implemented as an RC circuit. On the other side of it, you might say that, hey, I mean, I have a leaky integrate and fire neuron. I can make some approximations and say, hey, I'm not going to have the leak. I'm just going to have integrate and fire. So that's going to have more firing, but can I use that kind of a neuron? On the other side of it, the neuron can potentially be stochastic. And in fact, the reason I show that particular curve here is a stochastic sigmoidal function, is that we've been actually looking at magnetic tunnel junction as an example, which can potentially act as a neuron, right? And in fact, if you look at any switching of a nanomagnet, that's going to have a functionality which looks like this, right? Even if your barrier height is, let's say, 40 kT or so, it turns out that the switching is stochastic in nature, and if it's a sigmoidal switching like that, can I effectively use it as a neuron, as a sigmoidal neuron? Now, also, there are other kinds of activation functions that one can look at. Today's deep learning, if you're familiar with it, they actually use what's called the ReLU neuron, or it's a rectified linear unit. You need some sort of nonlinearity, and the nonlinearity comes from basically having that negative side be taken out. Or you can also think of a tan hyperbolic neuron. So these are actually the ones that are used today. But then again, more if you want to be more biologically plausible, and the reason why you'd like to be biologically plausible is because of the fact that it can be a means to an end of achieving better accuracy, better power consumption, and so on. So those are the ones which are shown on the left. Now, how do I train a neural network? The best way to train, and mathematically it's actually quite strong in terms of coming up with bounds and all, it turns out one can use what's called backpropagation. Or in other words, think about it this way, that if I actually have a neural network and I have parameters which are random in nature, let's say, the parameters are all random. If I show a cat as an input, the output neuron of the cat is probably not going to be active. So if it's not active, I find out what the loss. And if I find out the loss, then I can backpropagate through my circuit, figure out what the weight should be in order to make it to be a cat. Right? And that's what backpropagation does. So now what you have to do in backpropagation then is that since you're backpropagating, you have to have the activation function to be differentiable. And if it's not, then you have to make some approximations. And as you can understand, the leaky integrate and fire kind of neuron that I talked about, that is not differentiable, so you have to make some approximations. Otherwise, ReLU is taken, and ReLU is differentiable, and that's the reason today deep learning uses ReLU as an activation function. Sigmoid is, again, differentiable, so is tan hyperbolic and so on. So again, basic idea in backpropagation, you go back and forth through the network, figure out what the weights are going to be based on some of the gradients that you determine based on the loss that you get at the output. Now, that's actually quite expensive. It sometimes takes a long, long time to actually train your large-scale neural networks. You might have heard of all these, I mean, we all know about LLMs, right? The large language models, and the larger ones, we in the universities don't even have capabilities of, doing. It takes a long, long time. So anyway, is it possible to actually do some local learning? And local learning has actually been observed in the brain. So is it possible that I do some local learning? And again, I'm not going to go into the details of it, but it would suffice to say there's a good amount of work that has started to do basically local learning. And this is an interesting work that was done some time ago called random feedback connection. So rather than actually backpropagating this error through each and every layer, is it possible that I directly feedback that error through a random feedback connection to these different layers, and using that, can I learn? And it turns out you can learn, but for larger scale networks, it actually doesn't do a good job. So there are some, again, other variations of it which have been actually recently thought of, which are, again, more quite bioplausible. They can do larger circuits, but still not to the scale of what is required to do these large-scale LLMs and so on. All right. So the other option is, once I'm able to come up with the right kind of neuron functionalities or the learning algorithms, the next question that comes is that, can I make it more efficient? And as I said, if I were to take cues from biology, or in fact for humans, the way we do things is not to give importance to each and every pixel. One can do foveation. One can do saccades. So what are foveations and saccades? Now, in neuroscience, people talk about two streams and two separate streams in some ways. In the brain, one is called the dorsal stream, the other is called the ventral stream. The dorsal stream is actually the where stream, where the objects are. That basically guides the functionality. And on the other side of it, the ventral stream is the what stream. So what would that object be? And as you can understand, that is possibly related to somewhat like foveation. We have an area of the eye, which is called fovea, and we can have a particular glimpse, as I said, and I can look at a particular area, and the rest of the things are going to be blurred. So can I do efficient computation so that I can do better object detection and recognition? The next thing that is also important is to figure out where the objects are, right? So to that effect, it turns out, we do have these rapid eye movements, which are called saccades, and there was some good amount of experiments that have been done, which in this particular case shows for a particular human, again, everybody's going to be different, but for a particular human, that illustrates the eye movements in just 2 seconds of the observation. And those were the points of interest that they looked at. So with that in mind, so one can potentially think of, hey, is it possible that I'm going to do somewhat like a dorsoventral network, so to say. I'm going to figure out where the objects are and what these objects are. So in this particular case, I'm not going into the details of where the objects are. These are the points of interest that I have. In this particular case, a cat, a human, and a dog. And one can start foveating. As an example, I have a little patch of image that I look at, and I say, hey, what does it look like? So I prime my network in this particular case, and to be able to say it's possibly a cat's ear. And if it's possibly a cat's ear, then I'm going to look for the cat's mouth, let's say. So I'm going to move down and right. I need to know where the locations are, and that's what I also need to learn. That I don't expect the mouth to be on top of the eyes. That's an expectation, and that's what we learn. We know that learning, we always do a lot of learning in language. In language, it's actually easier. There's always a syntax and the semantics, and the syntax is easier to follow. But for example, in images, the syntax is actually a little bit difficult to follow. In fact, most of the time, if you don't have the right syntax, the deep learning gets fooled completely. You can take a face, break it up into 4 regions, put it on the 4 corners, put a tree in between, and it's going to say with a very high confidence it's a face. But such learning actually tells you, not only the syntax of the image, but also the semantics. So you move down and right, you have the sensors. Now your network is primed to say it's probably a cat's eye, right? You're not sure yet. You go further, expand, go down, and now, lo and behold, it's a cat, right? And you have a bounding box for the cat. So that's how you can potentially do. We applied it for the fun of it in our, using such algorithms in our group, and this is basically showing some examples of, we can recognize the people and figure out where they are, using both foveation and saccades. In each of those cases, you can figure out where the people are. Now, this also lends to something which is interesting. Now, most of deep learning can't handle this, but these are some of the optical illusions. The question is, what is it? Anybody thinks it's a rabbit? Yeah, some of you think it's a rabbit. How many of you think it's a duck? Okay, so most of you think it's a duck. How many of you can see it simultaneously be a duck and a rabbit? You don't. The reason you don't see it, we always prime our networks to be able to see something. We're looking for features, right? We don't see both the features at the same time. You can go back and forth and see it as a rabbit or a duck, but you don't see it at the same time. And that's exactly what deep learning in this particular, in our case, the foveation and Saccard's-Bates algorithm or the dorsoventral network can do. If you start there, it's going to be a rabbit. If you start there in a foveation, it's going to be a duck. Okay? And that's exactly an example of showing that, you can actually potentially show it's a rabbit or a duck by really having the right foveation points. Huh? So now if I actually ask my drone, go to the rabbit, it has to now foveate, figure out where it is, and then go to that, or if it's a duck, it's going to go to the other side, right? But today's deep learning can't do that when we humans are actually good at it. Huh? We always look for proper features, and so when you look at, for example, in the sky, patches of cloud, somebody says, hey, I see a human face. Huh? Somebody says, no, it's a dog, right? Why? Again, starting foveation points are different, and you're looking at different areas of that image. All right. So with that in mind, the next thing that one has to also think about is what should be the network architecture. That was the learning part of it, assuming I have a network architecture, right? So what should the network architecture be? So it's very difficult to know what kind of network architecture the brain uses. So as a part of our center, the Center for Brain-Inspired Computing, we had our collaborators, and this was actually done at MIT. In Professor DiCarlo's lab. So what they decided to do is that, hey, I'm going to look at these monkeys and I'm going to probe the monkey brain, and what I'm going to do is I'm show some images to the monkey, and if the monkey recognizes those images, then I'm going to give them a reward. Huh? And based on that, they looked at basically the actual ventral system, which has these layers, which are the V1, V2, V3 small, V4, and the IT of the brain, which is basically the visual cortex. And they try to figure out what are the activities there, right? And based on those activities, they looked at also a few neural networks, which are shown here. And those could be a VGG16 or a ResNet kind of network. And they tried to figure out that how well these networks, which are these VGGs or the today's the standard artificial networks, how well they do compared to some of the measurement results. And they try to do a regression to figure out which network is closer to what the brain does. And they found out that the networks, and again, they found out that the networks which are closer to what the brain does has possibly better accuracy. Very difficult to prove it because, they can't probe every neuron, right? They don't know the architecture. And they have to figure out where these activities relate to in which part of the layers of these artificial neural networks, right? But still they figured out, hey, the networks which are closer, so to say, in terms of what they call the brain score, if it's closer to the brain, the higher the brain score, then possibly a better the accuracy. Doesn't say much, but it really tells you that, hey, maybe can I now design neural networks which are closer to what the brain is and get better accuracy with a brain score. Still a long way to go, but sort of things are in the right direction to see if we can actually figure out these networks and how close they are to what these artificial systems are. So with that in mind, I haven't talked about the hardware. With that in mind, I can now think of, say, hey, can I use these neuromorphic algorithms that we've been developing to do a completely vision-based navigation? So what would be required in a completely vision-based navigation for a drone? As an example, if I were to go from point A to point B, first I have to figure out what's around me, right? And what are things moving, what are objects which are stationary, all those sort of things I need to figure out. And then the next thing I have to do is figure out plan a path to go from A to B without hitting objects or not even to hit any moving objects, to move away from moving objects and all. So how do I go from point A to point B? So to that effect, people do what are called optical flow, right? Optical flow is basically understanding, the things around you. Then you have to do segmentation, then you do, for example, object detection, track moving objects and avoid them. And finally, your actions that you need to take for the drone. So how do you start? You need sensors to determine what's around you. So what's your sensor? in this particular case, a camera. There are different kinds of camera. I'll talk about a couple of cameras that we've been using, which is a standard frame-based camera, or what's also called a DVS camera. Then that input that you get from the camera has go to this network, right? And that's your algorithm. It's going to be implemented in a network architecture. Now, all these different kinds of networks that I talked about, right? I talked about different activation functions, different ways of learning. That's going to be coming in here, right? And turns out some of these hybrid networks, a combination of these spiking versus non-spiking and all, turns out are the best. And at the end of it, you need a hardware architecture to do that. And that has to be implementing these algorithms in there. So very quickly looking at the camera, the frame-based camera versus an event-based camera. Frame-based camera we're all familiar with. It has different frames coming out, and I'm just showing a neural network that it can go through for optical flow, which is basically kind of like an UNet kind of architecture. But usually these cameras have motion blurs and they don't have high fidelity. But this is a DVS camera. Whenever there's a relative motion between the camera and the object, I produce a spike. Otherwise, nothing happens. So if there are no motions, nothing happens. So the output is 0. If there is a motion, and high motion in this particular case, as you can see, that you can actually have spike as outputs. So now we using these spikes, and the difference in timing between the spikes sort of tells you how the objects are moving and so on, and that you can now feed it to a spiking network and get interesting results. As an example, if you look at, for example, perception and optical flow or depth estimation, this is an example. I think I should. What we need to do is we have a 3D environment, and from the 3D environment, my eye basically has this retina, where the retina basically have these 3D objects which are mapped into the 2D vectors, 3D to 2D. Or in other words, the estimation of 2D motion field from the 3D that you see in the real world. And that's optical flow. And optical flow tells you now what's the environment is around you. And very quickly talking about such an environment, and again, I'm not going into it, but it turns out selecting or coming up with the right kind of network architecture is important. And not only that, a hybrid combination of really ANNs and SNNs can potentially give you a good architecture in terms of the number of parameters that you have, and also at the same time, the accuracy that you can get. Going further, what you need to look at, hey, what kind of hardware architecture that I need to look at? Again, not much time, but most of deep learning, if you're familiar with it, it turns out that you end up doing a huge number of matrix vector multiplication. You can do approximations. You can have stochasticity. I talked about the stochastic sigmoid operations. Those are all possible because you're looking at operations which are not, exactness may not be required. And a lot of times, for example, when you do search in the web, there's no one golden solution, right? There are multiple answers that you can potentially get. So again, stochasticity or approximations are okay. Approximations like 10 plus 10 is 20, but if I can implement my hardware to do 10 plus 10 to be maybe 18 or 19, but that gives me energy efficiency, why not? And the reason is very clear that when you learn, if you put such a hardware, when you learn, you not only learn the data, but you also learn the hardware, okay? And if you do that, you don't get an accuracy degradation. Okay? So those are the kind of things that you can do. And so that now, using these kind of approximations and all these in-memory computing that I talked about, hey, computation in the memory itself, you can potentially have really high energy efficiency and accuracy. So to that effect, actually, we looked at, as an example, for this particular problem of optical flow, we looked at a GPU-based baseline, which uses an NVIDIA Jetson TX2. And what we found is that implementing these algorithms in there, we couldn't even meet the constraints of having 30 frames per second computation. Okay? So you needed in-memory computing, and this is actually an implementation in our group of a 65 nanometer technology doing in-memory computing with sparsity that could go all the way up to 35 frames per second. This one is actually a spiking architecture going all the way up to and again, 40 frames per second or so. And finally, at the end of it, this was just a simulation showing that, some of the things that I didn't go into details of. If I do device, circuit, algorithm, co-design, and get rid of some of these extensive ADCs, the analog to digital converters that might be required, if I can get rid of it, then you can get a much, much larger efficiency. The last few slides showing that it's possible to do, implement these algorithms. This is actually one of my students a few years ago, doing gestures using a DVS camera, as you can see on the right side of it, asking the drone to go up, down, left, right, and so on. So these are the different kinds of, algorithms using these hybrid architectures that I talked about. This is an example of in our drone lab, using, again, very similar kind of neuromorphic algorithms that I showed. The drone is supposed to figure out at what speed the ring is moving, and then determining that speed, it goes through the ring and lands on the other side. So again, these are object tracking and figuring out the speed and going through it using these kind of interesting networks that we have. And in the front right here is a DVS camera. You might say, hey, why is the camera there? This drone is too light to carry that camera. That's why the camera is fixed in this particular case. And going, in fact, even further today, using foveation and saccades, and this is not sort of simulation showing it, that I can give large language models that can give you, for example, some sort of commands. I can say that, hey, I can ask the drone to go past the first traffic light, go straight past the blue car. And again, here I need to foveate, figure out where the objects are based on these input commands that I have. And then turn right, go to the stop sign, and land in front of the gas station. And this is, again, example of, and this is a simulation showing in the gazebo simulator, showing that the drone in the middle right here is flying through, trying to avoid objects and following the commands. And how is it following the commands? Using the eye and doing foveation and the saccades that we talked about. Just wanted to show you the kind of things that's possible today. And again, this is again a very similar example with a different kind of command. I need to leave a little early. Unfortunately, I have to give another talk in 15 minutes. But I just wanted to mention the fact that sensing, proper sensing, hybrid networks, that's the way to go to really come up with bioplausible way of learning. And why bioplausibility? As I said, it's a means to an end of achieving better accuracy, better energy efficiency. I didn't talk much about the devices, the neuromimetic devices. There's a good amount of work that we are also doing, looking at, for example, the magnetic devices versus the ferroelectric transistors to be, which are good synapses. How can we do that? There's a project that we have which started with ME Commons, which is called Cheetah, supposed to be fast and efficient, but it's going to be using magnetic tunnel junctions to do in-memory computing. And then stochasticity of these magnetic tunnel junctions to have stochastic neural networks. But all these sort of things, the bottom line today is that energy efficiency is absolutely important. So the question, of course, is the fact that, hey, can I take these algorithms, the different kinds of hardware possibilities, and the devices, co-design them to achieve the right kind of architecture. So at the end of it, I really feel that algorithm hardware co-design, guided by biological principles, can be a pathway to next generation neural computing. These are the guys who do all the work, and I get to go around and give talks for them, but they are the heart and soul of our group, and acknowledging our sponsors. Thank you.
This great talk. Do you have time for a few quick questions before you? It's a third. Okay. Do we have any questions?
So I was just curious. There's so many advances in neuroscience these days, and how much feedback from the developments in neuroscience and understanding brain pathways is fed into your algorithmic development? I just give you an example. I was at Stanford a few weeks ago, and a friend of mine as a neuroscientist, and they have this laboratory where they have mice, and they have multi-local probes. The mouse is alive. He's basically playing a video game, the mouse, and he gets a reward. But they're probing locally, and what the interesting thing is that we're seeing activity in places you wouldn't normally expect to see activity for a particular function. It was sort of, in my naive way of thinking of it, sort of distributed in a way you wouldn't have naively expect. So I'm just wondering, how much feedback is there from what's going on in neuroscience back into how you guys are trying to build better algorithms?
Very good question. There's some feedback, certainly, no question about it. But for example, if you to start with the standard deep learning network, are weakly inspired by the neural networks. They don't certainly have the activation functions of what most of these other neural networks are, the biological neural networks are. So we've been trying to do more sort of like, hey, can I be closer to the Hodgkin-Huxley model kind of thing? Or maybe can I do leaky integrate and fine neuron? And would they be more efficient in some cases? And in a lot of cases, what we found is a combination of things that you need to do. The hybrid combination of some of these can potentially be good. Another example is that dorsoventral networks that we talked about, right? In general, it's easy to fool the networks, and some of you have heard of these adversarial ones. I mean, you can take an image, you can add crafted noise to it, a little bit of crafted noise to it, and to a human, it actually still looks the same, right? But the network catastrophically, says something completely different, and those kind of things can be avoided now because I give now importance to certain pixels more than the others, right? So that way, I think some of these things about the dorsoventral are really coming from neuroscience and so on. Still a long way to go. We don't have the understanding. Still a long way to go, but the hardware certainly is always problematic, right? In the sense that the hardware is something that you end up using, the GPUs, the kind of computing power that you need to implement some of those. But if you want to go, for example, to these other routes of, in fact, even if you want to change and go to a ferroelectric transistors or whatever, it's not possible right away to do something large scale. It's going to be a few transistors here and there and doing it. RRAMs are sort of easier to do in a lot of ways, easy to fabricate. Everybody can fabricate their own RRAMs. But they have other problems, reliability problems, endurance problems, and so on. So all kinds of interesting things are there. Magnetic tunnel junction, to me, are possibly the most mature one, but they still have another kind of problem because the TMR is low.
Yeah, thank you. So maybe another question.
Thank you, Professor, for the talk. I have a question. I don't think it's like directly relevant, but do you think there's any bottleneck with like this learning task in which quantum computing can play a part?
I hear a lot, and I don't know how to answer because I don't understand it. I don't know what quantum AI is, if you can explain to me. But I need to learn from you. In general, if I were to really think about accelerating it, if I'm doing a lot of matrix vector multiplication, my understanding is that it's not suitable for it.
Thank you.
Hear from Professor Alam.
So it's a very nice talk. I learned by, sorry, go ahead.
No, I need to go ahead, another talk, no, go ahead, quickly.
Just in terms of analogy, I hear about compressive sensing and active learning. Is it related to the way the foveation and the approach you're working? Is it in some way you would say the mathematically it's similar or not?
I don't believe so at the moment, but we're trying to learn in some cases the syntactical features of the image and so on. So that's, sorry, I know that you also had a question, but I need to learn. You can ask me or send me an email. I have to give another talk in the Convergence building.
Let's thank Professor Roy again for the great talk. Thank you.